Let's get started by talking about gravitation. Here's a problem from one of our recitations that we didn't go over in class, dealing with orbital data. So we're given some information about Saturn, and we want to come up with an expression for the force between Saturn and its moons, the gravitational force. So a great way to start out is to say, okay, well, what do we know about gravitational force? Well, we know that the law of universal gravitation states that Fg equals G m1 m2 divided by r squared. And in this case, well, it's not too hard to just say, okay, well, if we assume that that's m of Saturn, and that maybe a lowercase m would be m of the moon, in our case, we could just say that the force would be this expression. So pretty simple. Using this expression, then, we have to say, okay, we have circular orbits, and we're trying to derive a period equation as a function of orbital radius. So first, we're paying attention to the orbital period of a moon. Well, that means the moon must be moving in a sort of a circle, so we should use our circular motion, our centripetal motion equation. M for moon, v squared over r, and that is the centripetal force, which is also equal to the force of gravity, which is g ms m over r squared from the above equation. Now, we'll notice that we get some cancellations here, and we'll get v squared v squared r equals gms. And we're looking as a function of orbital radius, so I should really move this over there. So we get v squared equals gms over r. And we can always take the square root to find the speed, but that's not the goal here. The goal here is to find the period. Well, it turns out that to find the period, we have, one moment, just to give us some more space. To find the period, we have some relationships. We know that we have period equals 2 pi r over v. And it turns out we have all these quantities, so really if I want to substitute in for v, I would say that v equals 2 pi r over t. And if we do that over here, we see that we have 2 pi r over t squared equals gms over r. And if we expand this out, we get 4 pi squared r squared over t squared equals gms over r. And if we want to move this to the other side, well, we get and we want to so let's say we get 4 pi, if with some algebraic manipulation I get 4 pi squared r cubed over gms equals period squared. And this is sufficient for solving this equation. It's a function of period or period squared. in relation to radius on the other side. And so if I look at this, what I want to do is I want to say that additionally I could take this value and put it over there. It doesn't really matter. Looking at this, what I see is I have some equation here for period, and it's equal to some equation here modifying my r cubed. So to make a straight line, I have to sort of graph this quantity versus this quantity, and everything else isn't a variable, so it's just sort of, these are constant values. So it's a constant in front, which represents my slope. So let me change color and say the slope of t squared versus r cubed, with t on the y-axis and r cubed on the x-axis. This would be the slope value. So when we find the slope, this is what we're finding. And so if we want to find another value later on, we have to keep in mind that this value is our slope. So we would say here t squared is the vertical axis, and then r cubed is the horizontal axis. And going forward, one thing that I want to pay attention to is, okay, now I need to complete the data table. Well, in this case, fortunately, I have this already completed, because otherwise it'd be a big old pain in the butt. So completing the data table, paste it there, move this graph down a little bit. And so if we look at this data table, you'll notice that I have the t squared versus r cubed with appropriate units, and everything in scientific notation, because these are some pretty big numbers. And now the goal is to plot this graph. And so how do I do that? Well, I should go down. I'll just plot it down here. Okay, so first thing I need to do, it's a little blurry, but I need to label my axes. T squared in what unit? Well, if we look at this, the period is in seconds, so this would be in the units of seconds squared. But because we want something reasonable, it should be 10 to the 10th seconds squared. And if we want to look at the period, or the r cubed axis, this is in meters cubed, but it's in 10 to the 25th meters cubed. Everything's modified by these values, so you should just have that to modify your axis, so that all you have to worry about is this number in front when graphing. So here we have 10 to the 25th meters cubed as the unit on that axis. And so if I go and I graph this, I will see that I go up to from 0 to about 6, and here from 0 to about 6. So, okay. So as you can see here, I have sort of gone through and talked a little bit about how I'm going to graph this. Last recording cut out. So what I'm going to talk about here is sort of the process I went through. First, you graph the axes, you graph the points, and then you draw a best fit line through. You choose 2 points on that line itself, and you find a slope. Now, the official slope is probably something on the order of, about 0.8 times 1 over 10 to the 15th. But I happen to eyeball it and get a slightly different value. You're never going to use the slope. Just finding the slope is not good enough. You have to figure out how that fits into your original equation. And here the original equation says that this expression here is the slope. And so I set that equal to my slope down here. And when I do that, I isolate the mass of Saturn, plug in values, and get some estimated value here. I encourage you to run through the math yourself. Just algebra, good practice manipulating exponents. So this problem is basically done at that point, calculating the mass of Saturn from the graph. Let's look at a different set of problems. Okay, this set of problems is going to be dealing with, and what we're going to be looking at is the equation for a simple harmonic motion of a spring. So let's say I have some spring attached to a mass. That spring is oscillating back and forth about some point. Now, the distance away from the point is going to be the k value. So we know for sure that we can come up with some sort of differential equation here. We know that we have it's the force of the spring, which is equal to the mass times the acceleration on an object. So if the spring is pulling left, then the object is going to be pulled to the left. If the spring is pulling right, the object is going to be pulled to the right. And so A turns out to be this expression, the second derivative position, with respect to time. And knowing a time value also lets us find acceleration values and velocity values and things like that. So the official equation might be something like, negative kx equals the mass times the second derivative of x. And so most simple harmonic oscillators are going to follow something like this. And if I gave you a graph here that mapped out the motion with respect to time, you'll get some sort of wave function. Now, if we look at this, we say, oh, well, what type of graph is this? At, say, maybe at this point is pi over 2. Maybe this is pi. Maybe this is, 3 pi over 2, and maybe this is 2 pi. And if we were to look at this graph, what I'd see is that at 0, I have a value of 0. At pi over 2, I have a maximum value. Maybe we'll say it's 1. Or maybe let's say it's 10. And at 3 pi over 2, I have a minimum value, maybe negative 10. And these are the values of displacement. So this might be my displacement versus time. So my displacement versus time graph looks like a sine wave. So this is pretty close to the sine of t, but it's not just the sine of t, it's 10 times the sine of t. So in general, the angular frequency term here, we should have an angular frequency term, which tells us sort of how how frequent our graph is. It's a multiple of time. So based on the values that we put in, we'll either stretch this graph out horizontally or we'll shrink it horizontally. And so that value is pretty important for determining when certain things happen in our graph. And so if we look at this in terms of just a general equation, we'll see that our position versus time can generally be modeled by a sine of omega t. And if I started somewhere sort of offset from the graph, I'd need a phi value, and that phi value is my starting position, starting time position. It's my angular frequency. And remember, this is all with respect to time, so the value that ends up, if I do a differentiation or integration, the value that I care about is the t value, the time value. And this is my a value, which is my amplitude. The factor of vertical stretch, how far away from the x-axis do I get? How far away from equilibrium does my object move? Now, if I want to find, this is also an acceleration with respect to time value, and so if I want to find that value to come up with something sensical for my equation, the way I do that is I say v of t is a cosine omega t plus phi. Then I do the chain rule on the inside times omega. And likewise, I can do the same thing to find a. A of t is negative a sine omega t plus phi times w times omega, which means just omega squared. We take this omega and multiply it by the omega from the chain rule, and what we get is omega squared. Remember, omega and a and phi are all constants, so they should be treated like constants when you differentiate. Now, I'm going to show you that this expression appears again in my acceleration. So that expression itself is x, essentially, x of t. And so if I wanted to say a of t is really negative x, if I have Newton notation, negative x times omega squared. Negative x omega squared, and I can plug that in on both sides, and I can see that that m of a is equal to negative k x. And so we'll see that we get some cancellations here. And we can see that I have those turn into positives. The x is cancel. So I get m omega squared equals k. And omega squared equals k over m. And I can always write this, and this is going through and finding the period of finding the period of an equation of an oscillating spring. So finding the period from angular frequency. Well, if we want, we can always talk about frequency equals 1 over period, and period equals 1 over frequency, and frequency equals so what we're looking at is a rotational or a circular translation of this. And what we can come up with is that, just like we see period equals 2 pi r over V, from this expression we can see that, well, omega r equals V, so V over r is omega. And so we see that this V over r is omega. Well, then we have 1 over omega here. So period equals 2 pi over omega. So 2 pi over omega is my period. And so if I get down to omega, I should be able to find my period here. So let's do that. Omega equals root k over m. But I know that period is 2 pi over omega, or omega equals 2 pi over period. So let's do that. So 2 pi over the period equals root k over m. And if I want to solve for period, first what I can do is I can flip both sides essentially. So period equals period over 2 pi equals root m over k, and therefore period equals 2 pi root m over k, and this is the period of an oscillating spring. So how long it takes for one back and forth oscillation, how long it takes to go, if this is my equilibrium point, how long it takes to go out to A and then back to this point. So if this is negative A, maybe it goes to negative A, and then it goes back to A, positive A, and then it goes back to 0, and that takes t seconds. Okay, so where t is the period. So going out, back, and then back. So from a graph, what would I see here? Well, I'd see that I can see for sure that my maximum amplitude is 10. So if I wanted to find a velocity value, I could plug in that 10 to my velocity, and I could see that omega is 1 here, and that phi is 1, and I could just say that the velocity with respect to time is equal to 10 cosine t. And 10 cosine t says that at pi seconds, what I'd see is a -1. My speed would be a -1 times 10, so that would be -10 radians per second. And you can do some conversion on that. Likewise, you can find acceleration at any point and position at any point. Okay. So finally, I'm going to briefly discuss one more concept. So the next concept that I'm going to look at here is the idea of work and just work and how work is related to displacement, and what it means to take a dot product and the like. So we know that work is equal to FD cosine theta. Okay, now why is that? And this is always going to be a scalar value. Just tells us an amount, never a direction. Although if we have negative work, it means the definition of work in general is work can be thought of as a transfer of energy, and a negative value can be thought of as a way from an object, and a positive value can be thought of as into an object. So in general, this is the idea of work. Negative work means we're taking energy away from an object, and positive work means we're putting energy into an object, or we're transferring energy into an object, or transferring energy away from an object. And so that has significance in a lot of problems that we're going to talk about. So to start out, let's say I have a block and I'm pushing it in this direction at an angle of 0 degrees, and I'm pushing it with 5,000 newtons, and the block moves across that time a distance of 3 meters, and throughout that entire 3 meters I'm applying the full might of my 5,000 newtons. We can think of this as saying, okay, well, all of the force I'm applying is doing useful work. It's lining up with the displacement of the object, so all of it is contributing to the motion of the object. And so in that case, the amount of work I've done, the amount of energy I've put into this object is 5,000 times 3 meters times the cosine of 0. And what's the cosine of 0? The cosine of 0 is 1. And therefore, I just produce 15,000 joules, or I transfer 15,000 joules of work into the block. Doesn't matter how heavy it is here. We're just considering the fact that I applied a force across some distance at some angle and produced or transferred a certain amount of work, or a certain amount of energy, produced a certain amount of work. Likewise, I can consider the fact that I have some amount of force downward. Let's say this is at an angle of negative 90 degrees, and I produce some force. Let's say it's 200,000 newtons of force. Let's say I have something really large, maybe an elephant or something, jumping on top of this car, or this object. Let's say it's a toy car of some sort, or no, let's say it's a go-kart. And I jump on top of this go-kart, and when I jump on top of it, maybe it has the engine going or something like that, it's going to go forward about 50 meters. Now these are some big numbers. So what do I know about this situation from a work perspective? Well, the work done is equal to 200,000 newtons times my 50 meters of displacement times the cosine of my angle. And if we solve this, we can see that the cosine of my angle should be equal to, well, cosine of negative 90 is 0. So that means that this entire expression is 0, which means we've done no work. So we've done no work. But the question is, how can that be? We've put force into the object moved. We put a lot of force, and it moved a lot. And so I guess the question would be, what does this mean for us? Well, it means first that the force that I applied really had no effect. The reason that the object moved wasn't because of the force I applied. It was for some other reason. Maybe it was from the engine and the torque on the wheels from the engine. Maybe we increase the frictional values, but that doesn't change the work. That just changes something that ends up coming into play later. And so we didn't transfer energy. We didn't transfer any useful energy. So the force that we applied had nothing to do with the displacement there. The force we applied was downward, completely isolated from a coordinate perspective, from directional perspective, from the direction of movement. And because they're not related to each other in any way, one didn't influence the other, we didn't transfer energy in the form of kinetic energy. We didn't transfer potential energy. We didn't do any of that stuff. Maybe we produced heat, but we're not tracking that right now. And so because of that, at an angle of 90 degrees, we did no work. Now let's consider the work that we do lifting something. Likewise, let's say I have a 10 kilogram box, and I want to lift it a height of about 5 meters. So I apply a force What direction is that force going to be? Well, it's probably going to be up. I apply a force upward. The object moved upward, so I definitely do some work here. If I'm not accelerating or anything, I know that the work I apply, the force I apply, has to be equal, at least equal to gravity. Why? Well, because otherwise this object would just be accelerating downward, and we don't see that here. So if the force I apply is equal to gravity, then I know that gravitational force is 10 kilograms times 10 meters per second squared, or 9.81 if you choose to use that number. So we get about 100 newtons of force that it takes me to lift this box. If I apply that 100 newtons of force, then that's across 5 meters, and it's at an angle of 0 degrees. Remember, the difference between this and this is the angle, so at 0 degrees still. Cosine of 0 is 1, so this is 500 newton meters, or 500 joules of work. Okay, so I have 500 joules of work that I did to lift this box. And so in general, the idea is that I have to at least be equal to the force of gravity. If I apply a force bigger than that, I'm going to be accelerating upward. I will do more work. But in this situation, all we know is I'm lifting the box. I'm not necessarily accelerating it. In our case, anytime we transfer energy to an object when we're lifting it, we're going to give it some potential energy. So if it has no kinetic energy at that point, all we're doing is we're giving it potential energy instead. So the transfer is a transfer of work from your muscles into potential energy, or work from an object into potential energy. Okay, so next idea is the following. So let's say I push something up a ramp, and I want to know the work done up the ramp. The angle is theta. I have some box, mass m, and I push the crate up the ramp, and maybe I have a force of 10 newtons. But the thing is that the object might slide down the ramp a distance of 4 meters. And so if I'm pushing up, and we can consider this the x-axis, if I'm pushing upward, my push goes up, but the object moves down. So this is my force, this is my displacement. Well, the angle between those two things, my force is this way, my displacement is this way, What's the angle between them? Well, it's equal to 180 newtons, or 180 degrees, because they're pointing in opposite directions. And that matters, because what it ends up saying is that the force goes in the opposite direction of my displacement. So it turns out I'm going to be trying to transfer some energy away from this object or something like that. I'm going to get a negative value. How do I know I'm going to get a negative value? Well, I have a force of 10 newtons. I have a displacement of 4 meters, but it's a negative 4 meters. It's 4 meters in the other direction. So you can think of this as saying, okay, well, I have, or I can just say I have 10 newtons times the magnitude of my displacement, which is, so this means magnitude in this case. Magnitude 10 meters times the magnitude of 4 meters in the negative direction, times the cosine of 180. Cosine of 180 is -1. So if I do this, because these are absolute values, I get 40 Newton meters, but it's in the negative direction. So I'm doing negative work trying to oppose this force, trying to oppose the displacement that this thing is making anyway. So I'm doing a negative amount of work because despite my pushing, the object moves in the opposite plane, or opposite direction. So while I may be reducing the energy of the object in that direction, in essence you can think of reducing energy of object in the downward direction. If I weren't pushing, it'd be going faster. If I weren't pushing, it would have gone further. And so we're in opposition to that. We've done some negative work. We've reduced its energy potential from what it had, or we've reduced the maximum velocity it could gain, or whatever we've done there. There's one more idea that I want to pass along, and this idea is the idea that, okay, well, what does it mean if I push down at some angle, let's say 30 degrees, on some block of mass m, and it moves 20 meters, and I applied a force of 100 newtons. So my force is 100 newtons. This 30 degrees is still, certainly it's a negative 30 degrees, so I could always say a negative 30. Well, yeah, I suppose I should rewrite that. So this is newtons. Let's delete that. Let's say from this point is 30 degrees. So it's a negative 30 degrees from the x-axis. And that just means that I have components down and I have a component horizontally. And the part that lines up is this horizontal component with my force and with my displacement, where my displacement is 20 meters. And so I have this negative 30 degrees. I have 100 newtons times 20 meters times the cosine of negative 30, but the cosine of negative 30 is going to be root 3 over 2. So in this case, I end up getting 200 over 2 times root 3. So 100 root 3 is my energy. And you can always simplify this to an actual number. Energy transfer. So I've done work. I've done work and I've done some energy transfer. And in that case, not all of my force is contributing to this motion, but some of my force is contributing to this motion. If we want to figure out how much force is in that direction, we just say 100 times cosine 30, negative 30. 100 cosine negative 30 is 100, so 50 root 3 newtons of force is in that direction. And the rest of my force is going downward. So that would be the rest of my force going downward. And that would contribute maybe to a frictional force or something like that, and we can do more complicated problems related to that idea. Okay, I'm going to call it for now. I'll be back later. Have a good time.